Hi everyone, so it's Joey here. I hope you're enjoying the course so far. So we've covered both internal validation and validation statistics today. And now that we've learned about those things, that sets me up to talk about sample size considerations for prediction models. So in this lecture, I will essentially split it into two parts. And in the first part of the lecture, I will talk about sample size considerations for model development. And in the second part, I will talk about sample size for validation of prediction models. And in the early part of the talk, I'll talk about existing rules of thumb and try to push us away from this and towards a more tailored approach. So if we want a useful model, then just as with any research study, just as for trials, we need to ensure that the study is designed well from the start. And sample size is one of the most crucial design elements, and yet it's often neglected in the prediction model literature. So we can see here a quote from a recent review by Paula Diamond saying only 9 of 119 studies, so 8%, reported a sample size calculation. And I'm sure you would agree that we would never get away with this in trials. So in general, when we're looking to develop a prediction model, we usually fall into two categories: prospective or retrospective studies. And I'm going to start by focusing on prospective. So when we're prospectively looking to develop a prediction model, we want to know how many participants do we need to collect in order to develop a suitable model. So what's the aim when we're talking about sample size for model development? Well, what we're really interested in is having a big enough sample to develop a model that accurately predicts the outcome that we're interested in. So remember that we've also discussed over the last day and a half the idea that when we develop our model, we should really use as much of our data as possible because we want to make sure that we build a good model. And as Richard mentioned earlier, we should really try to avoid splitting, whether that's random or non-random splits of our data, into a development and validation set. And this is because we believe that if you split your data to create a development and validation cohort, you're simply reducing the sample size that you have for developing the model. And this will eventually lead to overfitting. And on top of that, we're reducing the sample size for validation of our model. And then we're going to have an inadequate sample to evaluate the model's performance. So we won't be able to precisely estimate that performance. So at model development, small sample sizes can cause us a lot of issues. We might observe spurious predictor outcome associations, particularly when using selection methods. So some predictors that are important, that should be included in the model, could be missed, and predictors that aren't important may actually be selected in the model simply by chance, given the smaller sample size. We're also likely to encounter overfitting in small samples when assessing multiple predictors for inclusion in the model. We also know that if we've got a small sample size, our regression coefficients are not going to be accurately estimated, and often they'll be inflated. And this will lead to predictions from the model that are too extreme, and in turn this will lead to poor performance when we go forwards and validate the model in external samples, which is something I'll discuss in a bit more depth in tomorrow's lecture. So over the years, many studies have looked at sample size for prediction model development, and most of these have focused on the idea of EPV. Kim introduced the idea of EPV yesterday as the ratio of the number of candidate predictors relative to the number of events. So not the total sample size, but the events is what we're focused on here, and hence why we refer to EPV as a measure of effective sample size. Now, it's also important to note that in most cases, the number of predictor parameters we need to estimate in the model is greater than the number of variables, So for example, if we have a categorical variable with 4 categories, then we have 3 degrees of freedom and therefore 3 parameters that need to be calculated. And therefore, a more accurate name would rather be EPP, so events per parameter, or subjects per parameter if we're talking about linear regression. Across the many studies looking at EPV, many rules of thumb have been proposed for an appropriate target EPV for model development studies. But I think most would agree that the one rule to rule them all has to be the 10 EPV rule, proposed by Peduzzi and colleagues. However, in their paper on this, there's no real rationale from their results as to why 10 was selected. And I guess a cynic might think it was because we can all multiply by 10 in our heads. So these articles by Martin van Smeden here have now debunked this earlier work, and they're really worth having a read. As I said, we've got so many studies now offering different rules of thumb for EPV, and this makes perfect sense, doesn't it? I mean, why would one rule fit all scenarios? We don't see people in the RCT world saying that all trials need 100 patients per arm, regardless of the clinical area, regardless of the interventions. It just doesn't make any sense. And in reality, what does make sense is a more tailored approach to calculating sample size, specific to the problem at hand and the area you're researching. And these papers by Martin and others that have debunked this ethos have then led to a flurry of research in recent years looking to develop new approaches to estimating sample size needed for developing and validating clinical prediction models. So here we can see a selection of references, and I'm going to focus in on these two here that we published in Stats in Med, mostly because this is our methodology and because it's implemented in the PM sample size package, so it's easily usable. So these two papers focus on our proposal for calculating sample size for model development. And the aim is really for us to minimise the potential overfitting and to estimate key parameters in the model precisely. We've developed these calculations for linear, logistic and Cox regression prediction models. And the work really builds on much earlier work by Frank Harrell. So the papers cover a series of closed form solutions that allow us to calculate sample size to estimate key measures precisely. Let's think about these in a little bit more detail. Firstly, for continuous outcomes, the aim is to minimise overfitting and to calculate sample size that targets these 4 criteria. Firstly, a uniform heuristic shrinkage greater than or equal to 0.9. So this represents a sample size that would mean minimal overfitting and therefore minimal shrinkage required. The second criteria targets a small difference between the apparent R-squared and the adjusted R-squared. So again, this is a measure of optimism. Remember that the adjusted performance measure accounts for optimism in our development process. So if we target a small difference between these metrics, then we should have a very small amount of optimism. The third criteria is to precisely estimate the residual standard deviation. And the fourth, to precisely estimate the average outcome value, so essentially the intercept in the linear regression model. Now, in terms of binary outcomes and time to event outcomes, we again look at a series of criteria that attempt to minimise overfitting. So the first 2 criteria are the same. We look to minimise overfitting by aiming for a shrinkage factor greater than 0.9 and a small difference in the apparent and adjusted R-squared. Note that for binary and time to event outcomes, we need to use a different R-squared, the Nagle-Kirkes R-squared. And the third criteria for these types of models is to target a small margin of error in the overall risk estimate. So again, this is based around the idea of the intercept or the baseline hazard of the model. So obviously, as with any sample size criteria, we require certain inputs to be pre-specified by the researcher. And in this case, we need a set of 5 things. So we need to know the number of candidate predictor parameters that you're considering, the desired heuristic shrinkage factor, we recommend 0.9, but you might want to target a higher shrinkage factor than this. I'll talk about that at the end. We need an idea of the overall risk in the population or the average outcome value when we're interested in linear regression. And we also need some estimate of the residual standard deviation. But the really critical piece of information that we need is to specify what we anticipate our new model's R-squared or Cox-Snell R-squared might be. So this is the anticipated performance of our model. Now, a lot of the information here could be derived from previous studies and existing models in your field. For example, the overall risk and the predicted performance in terms of R-squared could be derived from previous studies. So as I said, the most crucial aspect is specifying what we expect the performance for our newly developed model to be in terms of R-squared. Now, as I said, usually we're looking for information from a previously published model. So if we're predicting for a continuous outcome, then we've got the standard R-squared over here, as Lucy described this morning. And this would usually be reported in any previous linear prediction model paper. However, it's a little bit more difficult when we're looking at logistic and Cox regression, because then it's the Cox-Snell R-squared that drives our calculations. And as Lucy described this morning, there are many different pseudo R-squareds for logistic and time to event outcomes, binary and time to event outcomes. So we could use O'Quigley's R-squared, Royston's R-squared, McFadden's, or Nagle-Kirkes R-squared. And PM sample size can at the moment take 3 different inputs. So either the Cox-Snell R-squared directly, if it's been reported in a previous study, the Nagle-Kirkes R-squared, which is more akin to the R-squared from the linear regression setting, so interpreted as a percentage, or the C statistic, which probably gets the award for the most commonly reported performance statistic in all of the prediction modelling literature. And Richard and Gary have published this note on estimating the Cox-Snell R-squared from a reported C statistic. And as I say, this is probably the most reported statistic for prediction models. So usually we will find this for a previous model in your field. And they use the relationship between the C statistic and the distributions of the events and non-events to estimate the Cox-Snell R-squared. And this is now implemented in PM sample size, so it's pretty easy to do using the software. So just a note here on the Cox-Snell R-squared. It's important to remember that the anticipated Cox-Snell R-squared for our new model could be quite small. And that's because, as Lucy said this morning, its maximum value is actually less than 1, as is calculated by this formula here. So we need to be realistic. If we're going to input a Cox-Snell R-squared into the calculations, it's essentially going to be driven by the outcome proportion. So for example, for logistic regression, if we had a 50% outcome proportion, the maximum we could achieve is actually 0.75. If we only had a 1% outcome proportion, the maximum Cox-Snell R-squared we could achieve would be 0.11. Just worth bearing in mind. Though now we can enter Nagle-Kirkes R-squared directly into PM sample size, and so we could avoid this. So one of the things we're often asked about is what to do if there really is no existing literature in your field that you can use to inform the parameters for the calculation. Well, the first thing I would say is go and look again, because there's an absolute pile of models in most research fields, as we'll talk about tomorrow, and we really don't want to be adding to research waste by building a new model. But if you really can't find anything and you're the first in your area, then we would suggest to use a Nagle-Kirkes R-squared of between 10 and 20%. And that's because in healthcare generally, outcomes are a low signal to noise ratio. So it's common to see R-squareds in the region of 10 to 20%. One exception to that might be if we've got predictors that are particularly strongly related. So for example, if you're trying to predict blood pressure and including baseline blood pressure in the model, then you might be able to achieve R-squareds of 50% or more. But we suggest going with an R-squared of 10% conservatively. So I've talked about the proposal now, and I just want to give a few examples implemented in my software package, PM Samp size. So again, this is for continuous binary and time to event outcomes, and it's implemented in both Stata and R with the same name, PM Samp size. And because it uses these closed form solutions that we've proposed, it's really, really fast. So first, there's a extensive help file in both Stata and R. So I'd recommend checking these out to understand the options and to see some examples. You can see here at the top we've got the general syntax for the command, and we can see that an important one is this first one here, type, which specifies the type of model that we're interested in. So let's just have a quick look at an example. So this is a binary outcome model. This is a paper looking at developing a diagnostic prediction model for chronic Chagas disease. So this is fairly complex, but also made fairly easy by the package. So let's build this example up slowly. So this is a typical output from the package. So we can see here initially that in the command line we specify the type of model that we're interested in, so B here for binary outcome. And then we want to specify the anticipated performance. So this is our Cox-Snell R-squared. And this is going to be the lower bound for what we expect our new model's performance to be. And this is taken from the previous study that we looked at that's developed a model in this area. So we need to specify next the number of candidate parameters that we're interested in. So in this case we're interested in examining 24 potential candidate predictor parameters. And then we need to specify the outcome prevalence. So in this case, again, based on previous literature, we estimate the prevalence to be about 17.4%. We can see then as we go down the page that the next element points out a summary of some of the preset parameters in the program. So remember I mentioned that we're going to assume a small acceptable difference between our apparent and adjusted R-squared. We're assuming a small difference of 0.05. We're also assuming a small 0.05 margin of error in the estimation of the intercept. And we're going to calculate the events per predictor parameter, assuming the prevalence that we've input is reflective of what we will see in our development data. So then the next thing we see is this printout of the sample size calculations for each criteria 1, 2 and 3. And we can see they are listed here at the bottom as a reminder. So in the table we have the sample size required to meet each criteria. We also have the shrinkage and the number of parameters. We then have the Cox-Snell R-squared that we imposed, which was 0.288. And then importantly, we have the maximum value of the Cox-Snell R-squared. So remember that the Cox-Snell has a maximum value less than 1. So in this case, based on the prevalence, the maximum that we could achieve is 0.603. We also have the equivalent Nagle-Kirkes R-squared output. And this is a lot more interpretable, similar to a standard R-squared for linear regression, so on a percentage scale. So in this case, given the Cox-Snell R-squared and the maximum we could achieve, given this set of parameters, we expect a Nagle-Kirkes R-squared of about 47.7%, explained variation for our model. I've also presented here at the end the EPP, so the events per predictor parameter. And interestingly, we can see that for this example, we actually require a lot less events per predictor parameter than the rule of 10. So again, this is just illustrating that a tailored approach is required to sample size calculation. So finally, moving down, we can see here we have a summary of the final sample size decision. So we take the maximum value of the 3 criteria as our minimum sample size required. So in this case, we can see that criteria 2 wins out, and it gives us a final sample size required as a minimum of 662 patients for our new development study. We can also see that this leads to a slightly higher shrinkage of 0.905. And finally, we can see down here that based on the prevalence inputs, we're expecting a EPP of 4.8, and we expect to require 116 events. So, as I said earlier, PM sample size can take 3 different inputs: the Cox-Snell R-squared directly, the Nagle-Kirkes R-squared, or the C-statistic. So I'm just going to quickly show the C-stat option using this study on a diagnostic prediction model for the presence or absence of DVT, deep vein thrombosis. And I'll talk about this paper a bit more tomorrow morning. So here we can see that they show the C-statistic for the previous development study as 0.79. So if we take this forward as the lower bound for the performance of our new model, then here you can see I have replaced the R-squared option with the C-statistic option. And PM sample size uses this C-statistic and the prevalence to calculate the Cox-Snell R-squared using a quick simulation approach. And the Cox-Snell R-squared is then fed into our equations. So you can see here we get an estimated Cox-Snell R-squared of 0.1809, and that is then input into our criteria calculations. So I've got a couple of slides here as well giving a continuous outcome model example, but I'm going to skip over these and just leave them there as an example for you to check out if that's the kind of thing that you're looking at. So I've mentioned this a few times, but it's very important to remember that the final sample size for our calculations is a minimum that would be required to develop a new model. And we say it's a minimum because there are many other criteria beyond those that we specify that could be important. For example, you might want to ensure that we've got precise estimation of particular predictor effects within the model. So for example, we might be interested in examining a few key predictors, potentially those with a low variance or low prevalence, or events in particular categories. Or those ones might require larger sample size to estimate precisely, and this then could inflate the sample size further. So far I've talked about sample size for prospective designs, but it's very common in prediction modelling literature for people to use an existing data set that they have to hand. And in this case, the sample size and the events are fixed, and rather you need to decide how many parameters you can realistically assess. And PM sample size can give you an estimate of this using the N option. So again, returning to this diagnostic prediction model for the presence or absence of DVT, the paper also gives us some baseline characteristics, as we can see here. So here we can see we have a fixed N of 1295, and we can use the C-stat of 0.79 as before. So first of all, you can see that we have entered the C statistic of 0.79 as before, and we've now replaced the parameters option with the N option. And we can see here we've got our fixed N of 1295. I also specify the prevalence from the baseline table at 22%. So we can see here now that for all criteria the sample size is fixed at 1295. And we can see that instead we're now estimating how many candidate parameters we might be able to consider. And we can see that in this case criteria 1 wins out. So this is driven by achieving a particular level of shrinkage, 0.9 in this example. And we can see based on the prevalence that we should have 285 events in our sample, and we can estimate 29 predictor parameters using this fixed sample size. So just to summarise model development before I move on to external validation, I've talked about how sample size has often been guided by these rules of thumb, but how it doesn't really make sense that there's one rule for all scenarios. Particularly I talked about the evil EPV10 rule and how that's been debunked now. And then I moved on to talk about emerging methodology, and particularly our sample size calculations and PM sample size, which implements these in a quite neat and fast way. So now switching gears to think about external validation. So again, it's equally important to get the design right from the start, and sample size is critical. But again, it's often being ignored in the prediction model literature. So here we have a quote from a review Gary did many years ago. An explanation of sample size was reported in only 9% of validation studies. Now, that's just really not good enough, is it? So now we're thinking about validation sample size. The question is slightly different. We already have a fixed model now. Instead, we're interested in having a large enough sample to accurately and precisely estimate the model's performance in the external sample. Historically, we had a rule of thumb for external validation studies of a sample size of between 100 and 200 events and non-events. And this was based on a few studies, including a resampling study that Gary led, a study by Vergao, and a study by Van Kalster that was focused on flexible calibration curves. Since then, we've developed a series of criteria similar to those designed for model development scenarios. So again, we have a series of criteria for continuous and binary outcome models. So for continuous outcomes, the criteria aim to calculate a sample size that targets, firstly, a precise estimate of the R-squared in the validation sample, a precise estimate of the calibration in the large, a precise estimate of the calibration slope, and a precise estimate of the residual variance for the calibration in the large and the calibration slope. And for binary outcomes, the four criteria again aim to target calculating a sample size for precise estimation of the calibration slope, the observed expected ratio, the C-statistic, and finally the net benefit. So you can see that the focus in both cases is now on estimating the performance statistics for the model in the validation sample as precisely as possible. And so I wrote PM_val_samp_size to implement this. So PM_val_samp_size calculates the sample size required for an external validation, aiming to meet these criteria for precise estimation of performance statistics. And the typical output will look something like this. So if we first just focus here at the bottom on the criteria. So we've got the 4 criteria for a binary outcome here, so precise estimation of the observed expected ratio, so a measure of overall calibration, precise estimate of the calibration slope, so a measure of optimism and shrinkage, precise estimation of the C-statistic, so a measure of discrimination, and finally a measure of clinical utility, precise estimation of the standardized net benefit. And again, there are detailed help files for the package, including references to the methods papers that will talk about these statistics in detail. So now focusing on the command line, we can see here it's very similar to PM_samp_size. We can see options here for the type of model, so in this case binary, the prevalence that we expect, the C-statistic. Here I should note that we often expect the C-statistic to be lower at validation, so we would recommend inputting a value about 0.05 lower based on previous review evidence. And one of the most critical elements for the validation sample size calculations is specifying the distribution of the linear predictor of the model in the new validation sample. And this is for criteria 2, estimating precisely the calibration slope. Now this is particularly tough, and we wish that there were better reporting of the linear predictor distribution in model development studies, as this would really help inform sample size calculations for validation studies that follow. So in PM_val_samp_size there are a number of options, including specifying a normal distribution, a skewed normal distribution. You can specify beta distribution for the predicted probabilities instead, as sometimes we can obtain these probabilities from calibration plots. This is then used to transform to the linear predictor distribution. Or finally, we can specify normal distributions for the event and non-event groups based on the C-statistic. Remember that this is the most commonly reported performance statistic. And in the next update to the program, we'll be able to specify separate event and non-event distributions for the other distributional options too. So we can also specify the graph option here for checking. So it's particularly useful to check the simulated distribution of the linear predictor against our source. It's also useful for reporting in the study so that future research has information on the linear predictor distribution we used. It's also got key statistics on there to describe the distribution, again for future research. So if we do look to use that LP C-stat option where we specify the C-statistic to generate our linear predictor distribution, then we need to specify 2 parameters, the C-statistic and a starting value for the mean of the non-events distribution. PM_val_samp_size then uses an iterative approach to find the appropriate parameters for the LP distributions, ensuring that the simulated data has a similar outcome prevalence to that you've specified. And there are some useful options to help with this in PM_val_samp_size too. So we can set the trace option to allow us to follow the iterative process, and we can also tweak it using options for tolerance and iteration step. But this option does make some strong assumptions. However, it might be our only option when we have nothing else to go on in terms of informing our linear predictor distribution parameters. Finally, just to mention that we've also published a simulation solution to calculating sample size requirements for external validation of prediction models with time to event outcomes. And this requires the user to specify the distribution of the linear predictor in the validation data, as before for the other calculations, as well as the event and censoring rates, and the target precision that we're looking for estimating the calibration slope in the validation data, and the particular time point of interest where we're looking at predicting for. And I hope to be able to implement this in PM val samp size in the near future. So in summary, for external validation, the focus with external validation is rather for us to achieve a sample size that allows us to calculate accurate and precise calibration and discrimination statistics. And historically, we've had rules of thumb suggesting around 100 to 200 events and non-events for external validation. But now we have some further methods that we can use to calculate sample size in a more tailored way for your particular example. So an overall summary. So I should mention some of the potential limitations to the approaches I've discussed. So one thing is around shrinkage. So remember that shrinkage really drives that first criteria in our calculations for model development sample size. And as Richard will speak about, shrinkage is actually estimated with particularly large uncertainty, as is evidenced by this quote by Van Hoingen. He says that while shrinkage works on the average, it may fail in particular unique problems on which the statistician is working. And essentially what he means is that when we have a small sample, and therefore when we really need shrinkage, it's actually in those circumstances that the amount of shrinkage required is estimated with a really quite large uncertainty. And so this is why I mentioned earlier that we might want to target a higher shrinkage than 0.9, and that this could then actually inflate sample sizes quite considerably. The next two things on this list here are issues that we've identified through people using the software in practice. So whether people are aware of it or not, they might inadvertently be inputting apparent performance statistics as the baseline for their new model performance, when in fact what we would rather like to have is the adjusted performance statistics from the previous literature. And secondly, as with any sample size calculation, these things are open to manipulation. So people often like to play with the inputs in any sample size calculation, in the trial setting, for example, as well, to ascertain a range of different sample sizes. And finally, I also want to mention that reporting is a big issue and can be quite limiting to our approach. So I mentioned that there are a number of things that we need to specify when we use our calculations, and so it's really important that the prediction model literature reports these things to aid in future research on prediction modelling. So let's make a plea here for you to report these things in your papers. So particularly when I'm thinking about sample size, it would be good for you to report the number of events and candidate predictors that you've included in your modelling, the number of candidate predictor parameters you considered, and also how you derived your sample size. For example, maybe you used PM sample size. It's also important to report multiple measures of model performance. As we can see, there are lots of ways that we can get to the performance statistics we need to inform our calculations. So reporting multiple measures of model performance is really useful for future research, not just a single measure of calibration and discrimination, for example. We certainly would like to see an estimate of the baseline survival, preferably at multiple time points, to allow future research to look at predictions at different time points. And indeed, if we don't have an estimate of baseline survival, it can be impossible for us to validate the model accurately. I've also talked a few times now about the distribution of the linear predictor. This has come up again and again through the slides, and it's something that's really important that it's reported. And also finally, to mention again the range of the predictor, so that we know whether we're potentially making predictions outside of the population in which the model was derived. And Gary will talk a bit more about reporting tomorrow. So finally, in conclusion, sample size is absolutely critical to avoid overfitting, spurious predictor relationships, and essentially poor performance in new patients. We'd recommend that you don't rely on old school rules of thumb and that one size fits all approach, and rather head towards a more tailored approach. And I've shown examples implemented in PM sample size. And finally, please fully report your development and validation studies, and you can use guidelines to help with that. And again, Gary will talk more about this tomorrow. So thank you for listening, and I look forward to any questions.